Hello students, before deriving the mirror formula, we will understand how the images are formed in spherical mirrors. So let us think of the images that is formed of spherical mirrors. We have two types of spherical mirrors. One is concave mirror, another is convex mirror. So let us take one by one. This is a concave mirror. Okay, this is a concave mirror, and this is the focus. This is the center of curvature. This point is the pole, and this is the principal axis. Now, what are the different types of rays that can come in? If I consider one ray coming from a point object is here, ray coming from this, that means from the center of curvature itself towards the mirror, then we know that any line joining the center of curvature to any point on the mirror, this point say P or suppose Q, then this is always a normal. So because this is a normal and along this line the ray travels, so it will be retraced, it will come back, it will be reflected back in the same direction. So the ray will be like that. So if I have a point object over here, then the image also will be formed here, because I will consider I should have more color for the images, but okay. If I call this as ray number 1, so in first situation your reflected image will be in this direction, it will pass through like this, and one ray I will consider from here, the ray traveling towards the pole will be reflected back in the same direction, because this is also normal. These two ray, one reflected from here and reflected from here, will met here, so image is also here. So here the object and the image will be the same point. This is how the ray will behave. If a ray I will consider is parallel to the principal axis, then any ray coming parallel to principal axis must pass through focus. So this will be the nature. So this is how the ray should move. Suppose this is ray number 2, this is ray number 1, like this. Let's pass through focus. And any ray coming through focus, moving through focus, any ray that passes through focus, this is the ray which is coming parallel, passes through the focus. But initially the ray is coming through focus like that, then after incidence it will become parallel, like that. Okay, this will become parallel. So this is how this is done, that this is 1, this is 2, I will call this as 3. This will be parallel. So ray which is passing through focus must be parallel, and the ray coming parallel must pass through focus. Here all the rays are real rays. The meeting point of this ray is here, the focus. Another situation is possible when ray is striking at the pole, okay, with certain angle. Then because this is normal, this is again normal, because to this point the center of curvature and this pole, this line is normal, this is also normal. So therefore it will follow the law of reflection, that is angle of incidence must be equal to angle of reflection. With the same angle here and here, it will be reflected back. This I will call it ray 4. So what will happen if a ray passes through center of curvature, it will retrace back. If a ray passes through focus, it will become parallel. Any ray become parallel, it passes through focus. Any ray striking at the pole will be reflected back like this. So these are the different 4 types of situation that we have discussed. So let us now take, this is the case of concave mirror. I will give you idea about convex mirror. Let us discuss about the behavior of those rays in case of a convex mirror. Let us see what happens in case of a convex mirror. In case of a convex mirror like this, suppose I have a situation like this. This is the pole. So this is a convex mirror. Now again, this is the pole, and center of curvature will be this side. Suppose that this is a focus, and this is the center of curvature. Sometimes this focus is called the principal focus. Now the rays, again we'll consider 4 rays as usual. One ray will strike here. What will happen to this ray? That will finish off with this diagram. Again, this is a normal, so it will follow this simple law of reflection. It will be like that. This is, say, ray number 1. The ray which is coming parallel to the principal axis like this. Suppose this is a ray which is coming parallel to the principal axis, must pass through focus in case of a concave mirror. Also, it should be in case of a convex mirror. But in case of a concave mirror, the rays are real rays after reflections. Here, and they pass through real focus. Okay, that is the real focus. Because the rays are actually meeting, real rays are actually meeting after reflection. But in case of this convex mirror, see what happens. It cannot pass through focus. It cannot pass through focus because the ray cannot go through this side, because this is silver. It cannot go to this side. But the property still remains the same. In case of a concave mirror, the rays are passing through focus. Here they appear to pass through focus. That's just a difference. So that is a case of virtual thing now is coming into picture. The rays coming parallel, striking the convex mirror, appear to pass through focus after reflection. So here is the focus. It cannot move like this, but it will move in this direction. If you extend this reflected ray in the backward direction, it seems to be meeting at focus. So this is how it behaves. In case of a concave mirror, it passes through focus. In case of a convex mirror, it appears to be coming from the, or appears to be meeting at focus. If I take one more ray parallel to this, this will also be like that. They appear to be diverging. In case of concave mirror, after reflection they are converging at a point. Here after reflection they are diverging from the point at focus. Now I will call this ray as second ray. In this second ray, the ray is parallel, and now it seems to be passing through focus. It seems as if it is coming from here. If I look from here, stand here and look at this ray, the ray is supposed to be coming from this side, which actually is not coming from this side. The ray is actually coming from this side. But if I stand here, I will have no idea about which direction it was coming. Because since it is coming in this direction, it will always appear to me as if it is coming from the focus. That is the meaning of this. That the ray is coming from the focus. Appears to be coming from the focus. In fact, it is not appearing to actually coming from focus. Therefore, this is how the terms are used. Now, if I have a ray which is directed towards focus, then which direction it will go? Suppose that I have a situation like this, that the ray is directed towards the focus. Any ray which is directed towards the focus must be parallel, because rays coming parallel appear to coming from focus. Now, any ray which is coming towards the focus, it will not pass through focus, that we know, because it has to be reflected back. It cannot move to the other side, it has to be reflected back. In what direction it will be reflected back? It will be parallel, always parallel. This is the third situation that we have. The rays coming parallel appears to be passing through focus, and the ray coming towards focus is parallel after reflection. You can see an interesting point here, that if you connect C to this point P here and extend this line, this is normal, and this is normal, and this angle and this angle must be same, because it will always follow the law of reflections. Okay. Now, another situation is, if the ray comes from focus, center of curvature, it is directed towards the center of curvature, then it has to be back in the same direction. That means if I move in this direction, then the ray will be reflected back in the same direction. This is ray number 4. Okay, this is how these are formed. This is how images are formed in case of a spherical mirrors. Now, let us derive one relation that is called with this I will just go on to derive the relationship between f and r by 2. So in this situation, the relation we will see between r and f. Now, you can consider any type of mirror. For the sake of convenience, I will always consider the concave mirror here. So this is a concave mirror, and this is principal axis. This is the pole. This is the focus. This is the center of curvature. Now, I consider a ray which is parallel to the principal axis. We must know that the rays which are very close to the principal axis and parallel are called paraxial rays, and rays much above the principal axis are called marginal rays. So these are the paraxial rays, but to distinguish the diagram, we have considered the ray much above the axis, but these are all paraxial rays. So assuming that this is paraxial rays, after reflections, as we have discussed just now, that all the rays coming parallel must pass through focus, so it has to pass through focus. This has to go like that. Okay. Now, if I join C with this point, say any point, say Q, I will join like that with dotted lines. This dotted line is normal, that we have already discussed. That if you connect a point C, connect a line with a point C with any point on the mirror, that will be always a normal. Now, if I call this angle is theta, because this is the angle of incidence. The angle of incidence is the angle between the normal and the incident ray. The ray will be reflected back with the same angle theta. This angle will also be theta. This has to be so, because angle of incidence must be equal to angle of reflection according to the law of reflection. Now, if I think of this line and this line, this line and this line, this angle is 2 theta, so therefore this angle will also be 2 theta, alternate angles. like that. This is 2 theta, theta plus theta. Here also it will be 2 theta. Similarly, if I consider this line and this line and this line, which one is the alternate angle? This angle and this angle is alternate angle. This is z over here. This is theta. Now, what is our aim? Our aim is to establish relations among this, how this r, radius of curvature, is related to the focal length. So this distance over here, from here to here, is the focal length, and this distance from here to here is known as radius of curvature. Okay, from here and here another radius of curvature. Okay, therefore, how I will have a relation between this length and this length, because this is x rays are parallax rays. This is very close to this. This is in fact like this. This ray, in fact, is striking the mirror at some very close points. This is Q. In this situation, you can imagine that this CQ is like this, and if you think of FQ, that FQ is somewhere like that. There is no basic difference. This line, particularly PQ, what I want to say is that this line PQ, which seems to be very magnified over here, seems to be very curved, is in fact is not very curved, because this ray is very close to this, and it will be something like a straight line, small straight line. You can imagine that this distance is neglected, and it is almost a straight line like that. This distance is neglected because of this ray being very close to this. Therefore, this distance, the actual curve distance or this distance, is almost same. The more and more the parallax rays are nearer to the principal axis, the greater will be this accuracy, and this distance will be very small. As the ray is very close to this distance will more approach towards the point P. Now, I have to relate directly with this triangle now. Now, you can think of CQP as a triangle. If you don't think of this as a triangle, you are insisted on taking this as the arc length, then also it's okay. We'll also define that way. But mostly this idea is considered, but you can take this still as arc length. We know that if you think this as arc length, then what conclusion you can do? This you see at here CQP from this C, Q and P. This angle is theta, and we know that arc length is angle is arc length upon radius. This is equation number 1. If I think of this triangle, this sector F, Q and P, this one, 2 theta. Again, I will use the formula that angle is arc length upon this radius, then also there is no problem. Now, from these two, we will relate the focal length and the radius of curvature. If I compare these two, I will write theta in place of theta here, or I can divide these two equations. So let us divide those two equations to get what? Dividing equation 1 and 2. Theta is PQ upon CP. Second equation is 2 theta is PQ upon PF. What we'll get? We'll cancel theta. This will become half. PQ will cancel. This will come to the denominator. This will go to the numerator. Numerator PF by CP. This implies what? What is PF? Look at the picture. What is PF? PF is this distance. This is the focal length. What is CP? CP is R. So we'll put these values over here. Half focal length by R. So from here, F equals to R by 2. This is what we are supposed to derive. This is the relationship between the focal length and the radius of curvature. So this focal length is half the radius of curvature. That is why we earlier took that to be double that of focal length, or the focal length is supposed to be half the radius of curvature. This is how they are related. Though we have derived it for taking concave mirror into considerations, but this is true for convex mirror also, and also for plane mirror. If I use dramatically, this is for plane mirror, focal length of plane mirror, because its radius of curvature is infinity, so focal length is also infinity, because F is R by 2. So this I apply to plane mirror, the focal length of the plane mirror comes out to be infinity, because when R tends to infinity, for a plane surface, the radius of curvature tends to be infinity. If radius of curvature tends to infinity, for plane mirror, what is the radius of curvature? Because this is a plane flat, so it goes up to infinity. R tends to infinity, so F equals to R by 2. So for a mirror, the focal length is, it tends to infinity, R tends to infinity, divided by 2, the whole thing tends to infinity. So focal length for plane mirror is infinity, infinite focal length. Interestingly, that we'll discuss afterwards in next videos, that the focal length of the mirror is independent of the plane mirror, is independent of the presence of the medium. Whether if I take a mirror, plane mirror, and place it in air, and suppose that whatever its focal length is infinity, if I place it inside water or any other medium, the focal length is not going to change, because it is independent of the refractive index of the surrounding medium. But if you think of the lenses, in fact, it is not going to change for any mirror, but when you talk about the lenses, the focal length is going to change. That we will see afterwards in next, not upcoming videos directly, but after some videos. Okay, thank you.